The next instruction covered in the manual was the move with mask. We always try to avoid this instruction because it's hard for people to troubleshoot it because it's not real apparent. It's not apparent what's going on. And every time you go to troubleshoot it, you have to go to the instruction help files and read about it and then go back and start analyzing it. And there are certain things that are hidden from you that take place inside of the instruction. They're there, they're part of the instruction, but you can't see them taking place, such as the masked result. In this next lab, for the mask move or move with mask instruction, we have a conveyor. And I realize this is a two-dimensional drawing, it's not 3D. So just to make sure that you are visualizing what I'm visualizing, at the entrance of the conveyor, there are two photo eyes. The entrance of the conveyor is to your left. Whatever is on the conveyor would go by those three proximity switches before it got to the photo eyes. So there is a relationship here between 1 PE, 2 PE, and those three prox switches. And those prox switches, they're inductive or magnetic, but they're going to sense metal. And obviously, judging by the size of them, you're going to have to be pretty close. And if you work with proximity switches at all, you know that the sensing range is usually not much more than the width of the face of the prox. A couple more illustrations. In the first one, we're looking at a tray. And if you're new to manufacturing, if you're new to material handling, you probably are wondering what in the world is a tray. Well, a tray is exactly what it sounds like a lunchroom tray. And product sets on the tray, and the conveyors move the trays around through the process. And the reason that they use a tray is because what you're placing on the trays may not travel well by itself on a conveyor or may not fit in a uniform fashion. These trays, we're going to make them identifiable. And in the first diagram, you see that at a specific spot on the tray, on the bottom edge there, which would be if you were facing in the direction that the conveyor is going, it would be on the right side towards the trailing edge. There is a mounting plate with ferromagnetic or ferrous type material buttons, which can be just a bolt head with a short threaded shank, and it threads into the block there. And there can be anywhere from no bolt heads to 3 bolt heads. And you'll see in the first tray there, when the first tray breaks the photo eye, in other words, breaks the beam of 1 PE, that the tray is in a position for the 3 proximity switches to sense the absence or presence of that ferromagnetic bolt head. In the second diagram, you can see that there is only 1 bolt head, so when it hits the photo eye, if your logic reads the state of those 3 proximity switches, it is basically encoding a value of 0 through 7. 3 bits give you 8 possibilities, 0 through 7. Now in this case, since you're sensing the tray, an absence of any bolt heads or a value of 0 is plausible. Typically you wouldn't use that because anything could block that photo eye, and if you're not sensing any bolt heads but you allowed for a 0, then if someone put their hand in front of it, it would read, of course, nothing and say that tray 0 is there. So each tray in my imaginary system has a pattern of bolt heads, anywhere from, we'll say, 1 to 3 total, and in different positions. And prox 1, prox 2, and prox 3, if you converted that from binary into a decimal, you would have 1, 2, 3, 4, 5, 6, 7 based on the position of the bolt heads when they were read. And of course you would do this with a one shot. We did call out Prox 1 as the least significant bit. So for the first tray there, now when I say the first tray onto the conveyor would be the one all the way to the right. But I'll just take the one that's right in front of the proc switches right now. If we were to read those three proc switches right now, we would have, and remember that prox 1 is 1s, prox 2 is 2, and prox 3 is 4s. If you add up 1, 2, and 4, you get 7. So obviously the first tray is going to be 1. The second tray, because you have 3 bolt heads, in other words the next tray to the right, that's going to be 7. And the third tray is going to be 3 because you have a 1 and a 2. The fourth tray towards the right from the left has a 1 and a 4. So that would be tray ID number 5. And the last of the 5 trays has a 2 and a 4, which means that would be tray ID 6. This little scheme allows you to have 7 trays going through your system, and each one of them has a unique bolt pattern that gets read when it first breaks the beam of photo I1 as it enters onto this conveyor. Now remember, we are working with the move instruction, specifically the move with mask. So in the upper illustration, you're moving, which is a word copy. You're copying the source to the destination. Of course, if the bit pattern in the source, and rather than just have bit patterns, I've converted it to decimal because it's too difficult to compare 2 bit patterns without going bit by bit. So the upper illustration would be a regular move instruction moving the bit pattern that represents decimal 25,989 from the source to the destination. Whereas the bottom illustration is a mask move. The move is actually mask. And the easiest way to remember the effect of the mask value is that in any of the 16 positions or 32 positions, if we're talking about a double integer, but in this case we're keeping it simple and showing 16, a simple integer. If there in the mask value, if there is a 1, then the value from the source will be passed on to the destination regardless of what it is, 0 or 1. Now you're probably looking there and you're saying, okay, in the source, the second bit is a 0, and the mask is 0, therefore it's not passed on to the destination, but the destination is 0 anyway. So we're talking about a value being moved into a destination, and if the destination reads 0, then basically you moved 0 into it. You can move 0 from a source to a destination, even though the destination was already 0. So you have to consider that the value that gets passed through the mask is all that matters to you. So if you look at the source, you look at the 3 bits that the 4th, 5th, and 6th bit, or we'll say bit 3, 4, and 5, they are 1. So in other words, that is the mask value, and it will pass on to the destination whatever is in those same 3 bits right up above it. Well, in this case, they're zeros. So the move did not change the value. The important point here for you to notice is that when this mask move executed, it moved the value of 25,989 from the source to the destination through a mask, but the result is that the destination is 0 because those 3 bits in the source bit pattern were zeros, and that's all that got moved, were the 3 zeros. And I did ask you a question here, discarding the value of 0, what is the lowest and highest value that the mask destination could be regardless of the source value? Well, the highest would be if bits 3, 4, and 5 were 1. And of course, it's an easy answer because the mask value is 56 decimal. So if all 3 of the bits that gets transferred are 1s, that would be the highest value. So the highest value would be 56. The lowest value would be the bit pattern of those 3 bits that is greater than 0, but the lowest value. So that would mean that the 4th bit, or bit 3, you have 0, 1, 2, and 3, bit 3, or the 4th bit. If that is 1, that is a value of 8. So the highest value is 56 and the lowest value is 8. How many different values, not counting 0, can the mask destination value, says not counting 0, can the mask destination value be as the source increases from 0 to its maximum? Well, we already know that. With 3 bits, you have 8 patterns of bits, but one of the patterns is all zeros, and since we're not counting 0, that leaves you 7. So the answer is 7. This rung of logic that I had you put in your program is real simple. It's got 2 move instructions, one with a mask and one without. The sole purpose is for you to be able to compare the value in input module 01 with the tray ID. So the move is just a direct move. Basically, you could say that we are buffering the state of the inputs from local 1I data into another tag called input module 01. But primarily, this is there just so you can compare the 2 values. To make it a little easier, notice that I changed the display configuration for input module 1 and tray ID. I simply did that by going to edit and then change this from decimal to binary and hit apply. This allows us to compare the bit pattern between the input module and the destination for both of these. Now I'm going to turn all of those inputs off so you see that the value up here, and remember that we're only going to work with 3 of these bits. We're going to work with 4, 5, and 6, which would be these 3 right here. But we could actually turn any of these on. You might be looking saying, well, why is the source and the destination different for this instruction? This one over here I might understand because it's got a mask. Well, this rung is not true. So as I change values in this input word, see, I'm turning values on and off. If I turn on input 0, of course, it's going to move it. But if I turn on any of these others, notice that these values are not seen down here, simply because that input is not on, so this rung is not true and it's not executing either one of these. Now we'll turn it on. Okay, and we're automatically going to have that input on right there because that's this input. That's the same memory location. Bit 0 of that data word, bit 0 of that data word. However, it's not going to affect our logic because we're not using that bit. Our mask value of 56, which you saw in the previous, would be with bits 4, 5, and 6 on. So only these 3 bits right here, 4, 5, and 6, are going to be seen down here. Over here, different story. You see it is shown. So right now you compare input module 1 with tray ID. This is still all 0. So I'm going to turn on those inputs one at a time. Now you see that both of these inputs are on right here. And our destination has a value of 3 decimal, still 0 over here. Turn on the next one. Now you have 7 here, you still have 0 here. Then we go to the 8 position. Now you have a bit showing up here. So this is 0, 1, 2, 3, 4, 5. So we have 6 inputs. We're using 4, well, 3, 4, and 5 on our simulator. If I turn on the next one, so you see the value here does not match the value there simply because, but this matches this, right? This matches local 1i data, and of course local 1i data matches this because they're both compared to the same thing. So this has got 5 ones and all zeros. This has got 5 ones and all zeros. If I turn on one more, now I have here a value, and you see that they're not equal. And I'm going to change them back to decimal to make it easier to see the value. So we can see the bit pattern easily if we look at it in binary, but the actual value is a little harder to follow. Okay, so these 6 inputs. Now watch this 63 here. These 6 bits all add up to 63. So 6 bits of resolution gives you 0 through 64. I mean, it gives you 64 patterns, 0 through 63. Now watch this value here as we change this value. First I'm going to turn off the second bit. So I turned off the 2, this dropped from 63 down to 61. But this stayed the same. I'm going to drop the next one. See, that drops down to 57, but this stays 56. So it is ignoring the first 3 bits. Now if I change any of the others, see, it changes both values. Okay, there you see an application for the mask move instruction. However, and those 3 bits don't have to be all right next to each other. So if you're trying to figure out how to calculate the mask value, let me show you. We'll bring up our programming calculator. If you haven't seen this before, you go to View, pick Programmer. Now you can we're only working with 6, well actually I'm only showing 8 here, but with control compact logics you could have 32. So you simply go in here and pick the positions that you want to unmask, in other words that you want to let through. So let's say I want position the 2nd bit, 3rd bit, and I want the 9th bit and the 12th bit. That's a decimal value of 2310. That's what you would put in here for mask value, and it would only pass through the state of bit 1, bit 2,